Okay, class, thank you very much for coming. Tonight we're doing a bit of a recording here, so I might seem a little bit rigid. However, I'm going to try and work it out so that we get through this lecture and you understand what's going on. Please, if you have any questions, put your hand up and I'm more than happy to answer where I can. Okay, all right, so this physics lesson here today is on the introduction to orbital mechanics. So we'll be looking at orbital mechanics. It's especially important these days because, as you know, the space industry is growing at a phenomenal rate. In fact, sort of at least around the $400 billion at the moment, and growing. So almost every country, significant country, has a space industry now. Australia has just started theirs, and that's going to be situated in Adelaide. And hopefully when you guys graduate sometime in the future, you'll be able to, some of you will want to actually work in the space industry. Okay, it's a very, very exciting thing to do. At my age, I'm working in the space industry and I don't have much time to go. You know, I'm 65 years old, so I might do this for another 2 or 3 years, but I think I'll probably retire after that. So this is an opportunity for younger people to take over and get involved. Okay, so this is because you people are pretty much beginners. This is a very introductory class in orbital mechanics, and then what we'll do is, as we progress through, week after week, we'll take this deeper and deeper so that you get a better understanding about how orbital mechanics works. Okay, all right, so we'll have a look at, these are the things that we hope to get out of this lesson. So what does orbit actually mean? What is it? T will be handy up there. Okay. Why are objects in orbit? What is the purpose of it? And what are other options that could be, and why don't we use them? Why is that we spend so much money? How does orbit work? Newton's laws of universal gravitation. We'll look very, very closely at Newton's laws of universal gravitation. We will have a look at the interface between Newtonian and Einstein's postulation for gravity. So the main things are in orbit for two reasons. One is the centripetal force, and the other is the balance between that and gravity. So we'll be looking at this interface between what Newton says is gravity and what Einstein says is gravity, and see how they actually comport, they relate to each other. Okay. All right. So first of all, what does orbit mean? So who hasn't heard of what a satellite? Okay. So satellites. Basically, an orbit means to have a path around a particular two objects, one of which has a path around the other. For instance, we have Earth, and that's probably not as, probably I want to make that quite a bit smaller. So let's call that Earth, and Earth will make a path around the Sun. Okay. All right. So it's almost, it's pretty much an elliptical path. So in other words, it's wider. It's wider here. So at some value of x, and this would then be, and this also would be some other value of x. So that there is a relationship between them, and the relationship between a for an elliptical orbit is pretty much x squared plus y squared, okay, over a squared over b squared equals 1. Okay, so we'll have a look at the mathematics between at this particular equation much later on. So, but for now we're just going to have a look at this. So orbit is things like the Earth going around the Sun. Can we think of any other major one that we see? Yes? Yeah. What sort of orbit do you see? At night time you see the Moon, don't you? Yeah, the Moon orbiting the Earth. And what else is there that you know about? Yeah. Satellites? Yes, the International Space Station, for instance. You know about the International Space Station? Yeah. Okay, so there are many things many objects that are currently orbiting the Earth. In fact, there are many thousands of objects. So at the rate at which we're putting things in orbit now, approximately at least one launch every 2 to 3 weeks. So you can see that is a lot of activity from the 72 odd agencies around. Okay, not all of them obviously involved in space, but there's also private agencies, there's private companies that actually put stuff in space as well. It's quite a lucrative business. Okay, so let's have a look at what an orbit is. So let's say, for instance, this is the Earth, and you are up here. This is not to scale. Nothing like it. Okay. If that was the Earth, the atmosphere would not even be the thickness of a piece of paper. Okay, so if you hold up a piece of paper like this, here's a piece of paper. If this was the thickness, if this was the size of the Earth, the atmosphere above the Earth would not be the size of the thickness of this piece of paper here. That's to give you an idea. Okay. All right. So this is obviously not to scale, but let's just say, for instance, we're over here and we decide we want to kick a ball. So we kick the ball, and lo and behold, we're not that strong, so we can kick the ball a certain distance, and what happens? What happens? It comes back down, doesn't it? Yeah. Yep. So if I throw the pen, what's going to happen to the pen? It'll drop. Okay? It'll form a parabolic path and it will drop. But what about if I kick the ball or I throw the pen even harder? Okay, so I throw it a bit harder and it keeps going. But it still comes down, doesn't it? Why is it coming down? Because gravity, yeah, because there is this attraction to the center of Earth. However, what if I try it again? All right, this time it's really, really hard. Still, not enough. What do I need? What do I need? I want this to go around to here. What do I need? Yeah, what do you think I need? I need to kick it a lot harder. Why am I kicking it harder? What do I have to overcome? What do I have to be better at?
To let it not hold on to it.
Yeah, I've got to be strong. I've got to have more energy than the gravity that's trying to hold this ball. That every time I kick that ball or I throw this pen, gravity's going to want to try and bring it back to the Earth. So I need to be able to make it go faster. Okay, to have much more energy. So let's say I do, and this time I am successful. If I am, I can actually toss that ball and it will, if I can do it fast enough, it will keep going. Okay, and it will keep going indefinitely. So this will go round. It's still falling, isn't it? It's still falling to the Earth. It's trying to get to the Earth. It's trying to fall to the Earth. The Earth is still pulling it in. Okay, but its velocity is so fast. Okay, it's so much that it keeps missing the Earth. It keeps going around and round because it misses. Okay, so in other words, it's falling in. And there's basically two forces here at stake. One is the centripetal force. So if you recall circular motion, we'll go through that again in some detail. So it's the centripetal force holding it in, and then there is that balance against gravity. Okay, so this is really interesting because when this was discovered that you could do that, of course everybody immediately jumped on the bandwagon and thought, wow, we could make some money with this. Okay, because we can actually make satellites go in orbit around the Earth, and we can actually get it to send signals back. Okay, that means that where once upon a time it was very, very difficult to communicate with let's say the people in England, who would have a hard time communicating with the people in Australia because it was so far away, and because of the shape of the Earth. Now this is actually quite a minor thing to do because we have such distances that the satellites are so far up, they can actually have a line of sight is very, very easy for anybody. Okay. Now there's quite a number of satellites around the Earth that are able to see practically half of the Earth at once. And the one that's over Australia, for instance, is the Himawari 8, which belongs to Japan, the Japan Space Agency, and they own that. And we in Australia, we use this satellite to be able to have a look at our part of the world. So in other words, Australia banks smack right middle there, and we can always use the satellite for our weather and the like. Okay, so you can see how this orbit works. I'm not going to get into the mathematics very deeply tonight, but I just want you to get an appreciation of it. But we'll do some exercises and make sure that you know what's going on. Okay, so I'll come back to Newton's laws of universal gravity, but we need to talk a little bit about gravity, what it is. Okay, so at the time that Newton came up with these laws, and these came from many hundreds of years, and in fact people like Galileo, who observed things, like Kepler, who were looking at stars and planets and seeing how they behaved. So, wow, I wonder why they do what they do. Why is it that they orbit each other the way they do? For instance, they noticed that Venus, the planet Venus, crosses between Earth and the Sun. So if a planet is crossing between Earth and the Sun, what does that tell you about? What can we learn from that exercise? We can see how fast it's going around the Sun, which gives us a pretty good idea about what the orbital distance is from the Sun, which then is able to tell us what speed it's doing, and all of these. So once they observed these things, we're able to come up with some really good equations that could model this movement. Okay, and that's pretty much what they did in the very, very early days And then Newton came around and put all of this stuff together. In fact, we owe so much to Newton, because not only did Newton actually put all this together, but Newton put the means for us to describe it together in a way that there wasn't there before. For instance, the calculus. Okay, so differentiation, anti-differentiation, integral, all of this is thanks to Newton's work. Okay, so let's have a look at this and have a look at Einstein's idea and Newton's idea. So Newton didn't actually understand why things fell. Why does this pen fall? He knew that it did, and he was able to calculate that the fact that this pen accelerates. So in other words, it goes faster and faster and faster and faster the closer that it gets to from here, the closer that it gets to the ground. So he knew that, and they could work that out, and that was pretty handy. Could make lots of really good predictions based on this. For instance, one of the important ones in wars was ships would fire a cannon from the ship. Let's put that over here, and that's the target. So cannon, they could work out a trajectory so that if you shot a cannonball out, you didn't have to guess. You didn't have to say, gee, I wonder what angle I'll have to raise the cannon for, and so that I can hit this target. It was not necessary to guess this, okay, because once gravity and projectile motion was understood, then it was quite easy to predict, to form an equation that would predict exactly how much angle would you need to raise the cannon, what sort of velocity would you need, so in other words, how much powder, how much explosion would you need behind the cannonball, how much would you need to create sufficient velocity and sufficient height to be able to accurately hit that target. It wasn't by accident. It wasn't guesswork at this stage. So projectile motion was very, very well understood. Of course, there were some issues with this, even though they understood, how to calculate that. By the time they had done the calculation, the enemy had moved, which wasn't very handy. And thankfully, when they thought about this, they developed computers, for instance, later on. And really, that's why the first computers were even invented. The computers were actually invented as a wartime tool. In other words, to be able to work out quickly this equation, Newton's equation, to work it out quickly so that they could actually aim at a target before the target moved away, or to be able to predict in a given amount of time where that target will be, say, in so many seconds' time. Okay, so Newton had some marvelous equations that made fantastic predictability. However, back around just after the turn of the century, a scientist called Albert Einstein, who decided that it wasn't good enough that we knew how to use gravity. We didn't actually understand properly how it worked. Why does the pen fall? It falls, we can't argue with that, but we've got to ask ourselves, why does it do that? And why does it do it in such a predictable way? For instance, Galileo worked out that no matter what size this is, and no matter what size the other object is, no matter what the mass is of this and the mass of that, as long as the friction of air doesn't count, they can both overcome the friction of air, they will fall to the ground at the same time. So, if I drop these two things from the same place, and they both subject to the same amount of friction from the air, they will hit the ground at the same time. Okay? If you put them in a vacuum chamber where there's no friction with respect to air, then they will always hit the ground at the same time. And in fact, there's a very, very famous film which I would encourage you to watch, for those of you who haven't seen it yet, where Professor Cox, Brian Cox from the UK, is dropping a feather, a bunch of feathers and a bowling ball in a vacuum chamber, and true to form, exactly as predicted, the feather and the bowling ball hit the ground at the same time. Okay? And the reason that they do that is because gravity is the same for all objects. For all objects with mass on Earth, it's the same. So at the same place, at the same elevation, gravity is the same value for all objects. In other words, its mass has nothing to do with it, except that gravity obviously needs mass to interact with. So Newton came up with his law, which is the second law, F equals ma, and where A is equal to G, and G is calculated at 9.8 meters per second squared. So this turned out to be a constant on Earth. So whenever mass was influenced by gravity, in other words this, okay, it produced a force, and this force was completely and utterly predictable. Okay, this was the amazing thing that Newton developed. However, as I pointed out before, along came Einstein and said, "Look, thank you, Mr. Newton. That was amazing work you did. In fact, Newton was a hero of Einstein, just like a hero of mine, actually. He's one of the giants on which I currently stand, on his shoulders. Okay, I couldn't do the work that I do as a physicist, except for the fact that I stand on the shoulders of people like Isaac Newton." Okay, so what happened here? Newton really had no idea, and Einstein, in his postulations, worked out how gravity works. And in a sense, it's like this. It's something that's not easy to actually represent on a board or in 3 dimensions. It's particularly difficult in 3 dimensions. But in 2 dimensions, it's reasonable. If we have, let's say, a mat, okay, and if you put a large ball, a large object on this mat, but there, it pretty much creates a well. Okay. So it creates a well around it. So you can see that it will fall into it. Okay. This is just from, if you like, from a 2-dimensional point of view. You've got to realize that this is happening in 3 dimensions. So that all around it, this well that's around here, isn't something that's something like a carpet. Okay? This is in 3 dimensions. This is happening all around this object. Now, if another object, so this object has some mass associated with it. If another object, we'll call that mass, call that M1 for mass 1. If another object comes close enough to this, then that object gets influenced by it. So we might have an object over here. Okay, so we have an object over here, and this object is influenced by this one. It will want to fall towards this larger object. It will then make a path around it and head towards it. So in other words, it's really a geographical phenomenon. Okay, so there isn't some magic. The model suggests there isn't some magic there that's pulling it. Like, for instance, if I dropped this, is there something that's pulling it down in between these two things? You could hardly describe it as that. In this model, it's the fact that this one here is larger than this one, and therefore creates this well in what's called, this here is called space-time. And the reason it's called space-time is because of this interaction between space, that means position, and time. So this interaction between position and time, so position as in a three-dimensional position, and also time, so this is called space-time. It's the bending of this space-time that causes this object to move towards that. Now, as you know, we don't just say things. Einstein didn't just make this postulation and everybody said, whoa, that's fantastic, that must be how it is. That's not how science works. Okay? When your turn comes and you end up doing some research, which I hope you will, okay, especially you can start doing that in your honours. So you graduate from your bachelor's degree and then do your honours and then get involved in some of this research. Well, you might come up with a very nice hypothesis, okay, and but no one's going to accept it unless you manage to show them how your hypothesis can be backed by evidence. Okay, so what happened here? This postulation by Einstein was actually backed by evidence. One of the most famous pieces of evidence. So this happened over many, many years, and one of the most famous pieces of evidence was carried off by a scientist called Eddington. Now, what happened was that this experiment could only be done in an eclipse. Okay, because there was no way to look at the sun. The sun was so bright, there was no way to see stars behind the sun by looking at the sun. So if there was any stars that were close to the sun, you couldn't see them. All right, because the sun is just too bright. There's no physical way to do that, and even filters and that couldn't do that adequately, because if you filtered it, then you filtered out the actual stars as well. So it seemed an impossibility. But there is one time when it's possible, and that is in an eclipse. This is where the light of the sun is pretty much blocked out. Okay, and because of that, it's possible to see the stars that are around the sun. Okay, so what Eddington did was, they worked out that there would be two stars that would be impossible to see because they would be behind the sun. So in other words, the sun is in between those two stars and us. It would be impossible to see them. So the hypothesis was, if you could see those two stars, which were theoretically impossible to see, if you could see them, that means the only way you could see them is because the light bent around the sun. So the light bent around the sun, that allowed you to see those two stars. Otherwise, they could not be seen. So in a straight line, impossible. The sun was directly in front of them, of those two stars. However, there they were, eclipse ready, and Eddington and his crew managed to have a look, and lo and behold, they spotted those two stars. Well, that was a major, major, major change for all of physics and all of science, because what it did was give us this definitive evidence that Einstein was correct, and that is that gravity, that sun was able to bend the light. Okay, so gravity was able to bend the light around the sun. Okay, so this then became the model for how gravity works. Of course, when I say it's a model, that's what I mean. You still have an opportunity to point out that maybe, just maybe, even in spite of all of that evidence, Einstein could still be wrong about how gravity works. That's still possible. Okay, so the thing about science is, we don't believe in truth. We don't say, this is the truth. This is it. This is the truth. And the reason that we don't say that this is the truth is because we expect things to change. If we said, this is the truth, Einstein's work is the truth, it's the fact, it's the truth, that means it will not change. Truth doesn't change. It is what it is. But that's not what happens. This changes. Okay? This becomes better and better as a model as we learn more and more about it. And because it changes, you can't call it truth. Okay? An example. There was a time when people thought the earth was flat. Okay? They thought everything was on a plane, the earth was flat, and that the sun and that went around the earth, hovered above the earth in a circle. Of course, they couldn't explain how the sun did that and where the energy came from for the sun to do that. That was a whole list of problems, associated with the fact that they thought the earth was flat. But anyway, they did. When the evidence and better instruments started happening, they then realized that in fact the earth is not flat, the earth is spherical. But they thought it was completely spherical. They had no idea that it wasn't exactly spherical. It's only after better instruments, more research, better ways of measuring it, that it was realized that the earth is in fact oblate. The earth is kind of flat at the poles. So it's not exactly a circle, so it's close. Like you wouldn't be able to see the difference. The difference is far too small to see it. So when we do look at the Earth from let's say from the Himawari 8 or other spacecraft that are high enough to be able to see the entire, it looks like it's a sphere. It looks like a sphere, but we know that it's not a sphere because we can measure it. We're down here. We can actually measure this Earth, and we know that it's not a sphere. So here's an example where once upon a time people said, well, that's the truth. The truth is the Earth is a sphere. Well, turns out that wasn't the truth. It's not exactly a sphere. It's an oblate sphere. And then it wasn't that long ago that they realized that, hang on a second, not only is the Earth flattened at both poles, but it's actually wider in the south than it is in the north. So it's just by a few kilometers, but it is. It's actually wider. So it's going around the Tropic of Cancer in the northern hemisphere is actually a shorter distance than it is going around the Tropic of Capricorn right here where we are. Okay? All right, so what about this interaction between Einstein and Newton then? Does that mean that we just forget about what Newton said? And the answer is, of course not. Because the work that Newton did works. We use it to this very day. We use Newton's equations right now. And we use them with incredible precision and predictability. Let's have a look at how they can intersect. How can we explain that they intersect? So, when this small object goes into the well, into this area here, and really gets drawn in by this large one, at this level, it looks like what's happening. This is being drawn into the well of this large object. But what does it look like in reality? This same phenomenon that's happening here, in reality, when you look at it, you don't see this. You've got no way to see this. Seeing this has only really happened with the experiments like Eddington, by the way, which was repeated many times. This was viewed from people like Eddington. But what do you see? You, as an individual, you see this. That's what you see. You see objects being drawn towards the Earth's center of mass. That's what you see. So, while this is what's happening, your observation of this is represented by this. Okay? So there is a clear interface between what Newton's observed, what Newton calculated. There's a clear relationship between that and what Einstein did. In fact, we can show this to be the case using formulas, both what Einstein produced and what Newton produced, and they match each other. That could not happen unless those models were extremely coherent. Coherent meaning they follow each other. Okay, that could not happen except for that fact. Okay, let's do a little bit of mathematics tonight, and I've got a sheet there for you to do, so you can do it. So let's have a look at some examples of this. First of all, we'll have a look at Newton's main equation for universal gravitation. Please make sure you've got this in your notes. All right, so this is what you're going to need. So the force of gravity is equal to a universal constant. As you know, it's proportional, so we'll say it's proportional to the mass of one object, let's call it the large one, times the mass of the small one over the square of the distance between them. Now, this inverse square law is extremely wide in physics and in how we observe the world. So it happens for light, happens for radiation, which is light, it happens for gravitational, happens for electric fields. Wherever there are these fields, there is this law prevails, which is the inverse square law. Now, this is a proportionality. When we talk about a proportionality, as you know, in mathematics, that means that for us to make this equal to this, we need a constant. We need to develop a constant. Okay, and this constant is called G. And because we now have a constant, we now have what's called an equality. So we now say that the force, gravitational force, is equal to this constant G multiplied by the mass of the large one times the mass of the small one divided by the distance between them squared. Okay, so this is essentially Newton's law of universal gravitation. So, in the last class where I demonstrated this, a student asked me, and obviously you'll have the same question: what is this constant, and where does this constant come from? Okay, so this constant was developed by experimentation, and probably the most famous of these experiments that was conducted by Cavendish, which you know about because this is one of the things that we do quite often. So you can go to the lab and you can actually do this experiment yourself. So this particular constant was calculated by this scientist called Henry Cavendish, and this is a particularly difficult experiment to do, and still is, as you know, because you have to be able to take a lot of things into account. For instance, how do you measure gravity between these two objects when the Earth has an influence on it already? Okay, so the Earth is influenced. How do you stop the Earth from influencing it? How do you stop all sorts of things? How do you show that it's not electricity that's causing these objects to come together? Okay, so there's a whole host of things, and I know that you're aware of this experiment. Go through it. You can have a look and see why it is that we rely on the evidence from this. Anyway, it produced this constant, and the constant is 6.67 by 10 to the minus 11, which is an incredibly small number. And because you can derive this formula, the force, if you're given the force, you can work out any of these values, including the constant, if you needed to. If you knew the mass, knew this mass, that mass, and the distance between them, and the force that's applied to it, you could calculate this constant. And of course, that's done. All right, so what I'm going to do now is I'm going to hand out the sheets for you, and I want you to have a crack at using this. While I come around to have a look at how you go, and you can ask me any questions you like about what we've covered so far. Okay, so let's see. I hope I produced enough of them. Okay, here we go. Tried to print them on separate pages. Okay, here you go. All right. This one. That's two. There you go. That's yours. All right. Okay. All right, so let's just have a look at this paper. Looking at question 1. 2 spherical objects will have masses of 200 kilograms and 500 kilograms. So let's have a look at this together, and then we'll do this first one and make sure that you're following this correctly, and then from there on you can have a look at doing the rest of these yourself. Okay? All right. Has everybody got this? Everybody written this down? Yeah? Okay. We don't actually need this anymore either. We're okay with this as well? You've got all of this? All right. Okay, so 2 spherical objects. Now remember, just a point, when the exam comes, anytime you do an assignment like this and when you're doing an exam, make sure, you're right, did you get one?
No, yeah.
Okay. All right, make sure that you use drawings, okay? All right, make sure that you do drawings, because this gives the examiner an idea that you understand what's going on. You can see what's going on. Even if you make a mistake, okay, the examiner is able to say, well, you understand what's going on, but you pressed the wrong button or something like that on your calculator and made a mistake, or inadvertently put something the wrong way around. But that becomes plainly obvious to the person who's looking at it. Says, look, I can forgive you for making a mistake like this. Everybody can make a mistake. That doesn't mean you don't understand what's going on. The purpose of examining you is not to see if you are any good at doing calculations. We fully expect that you do know how to do calculations and that you know the mathematics. You wouldn't be here if you didn't know the mathematics. All right, so we fully expect you to be able to do that. So I'm not here to test your fluency in mathematics. I'm here to test your understanding of the models, okay, and your application of those models. All right, so let's go. 2 spherical objects. Okay, 1 and oops. Let's try and do a better spherical than that. How's that? It's pretty terrible. Okay, and another one. Okay, 2 of those objects. Okay, have mass of 200 kilograms. 200 kilograms, and 500 kilograms. Well, this one is obviously a lot more dense. Okay. All right, let's talk about what constitutes mass. Now that from the lecture that we did in chemistry last week, remember about mass? All right, so remember have you got your periodic table here? Okay, let's have a look at potassium. What's the atomic mass of potassium? 30? 39. It's very, very close to 40, isn't it? Right? So let's just call it 40 for the sake of it. So potassium, okay, atomic mass. So atomic mass is equal to 40. 40 grams for every mole. 40 grams for every mole. What does that mean? Okay. First of all, the mole is a quantity. And we know this because the mole is a certain number of particles. It's an absolute number of particles. Okay, we know what it is. Well, when I say absolute, I don't mean that it's the number I'm going to give you is exact, okay? But it's close enough for what we want, what we need to do. So we can say we have a number of particles. We know how many particles there are. And in fact, the number of those particles is 6.02 by 10 to the 23 particles, okay? So we know that 40 grams of sodium has this many particles. This many atoms makes up 40 grams of sodium. So, we've got to ask ourselves, what does it mean by mass then? What does it mean by 40 grams? What does the mass actually mean? Yes. So what we're saying is the mass is every atom. Let's pick the smallest one. Hydrogen has a proton. In this case, this is just normal hydrogen. If we had heavy hydrogen, we could have a neutron as well. So this is a proton. What can we say about protons? Number of protons is the atomic mass, is the atomic number, yes? Yeah, good. Okay. Protons are all the same. Everything is made of the same stuff. This proton is the same as that proton. The proton in mercury is the same as the proton in iron. The proton in carbon is the same as the proton in gold. A proton is a proton. So what makes one thing different from the other? How many? If you're clever, you can have a look at how many protons there are in lead. How many protons are there in lead?
82.
How many? 82 protons in lead. How many protons in gold? 79. 79 protons in gold and 82 in lead. What is the difference between lead and gold? 3 protons. That lead turns into gold by removing 3 protons. That's it. Gold turns into lead by adding 3 protons. Protons are protons. Neutrons are neutrons. But the thing about these protons is they have mass. and the mass is the same for every proton. And if you have enough protons, 6.02 by 10 to the 23 of these protons, and put them all together, you're going to have 1 gram of hydrogen. If you have 40 grams of it, that means you've got how many protons? How many protons are there in potassium? 19. 19 protons make up potassium, plus the neutrons, comes to this 40 number. Because the neutron, if by virtue of the fact that the protons weigh, that many protons weighs this many grams, what does that also tell us then? The neutrons weigh the same as protons. So neutrons and protons weigh the same, and all neutrons are the same. What's the difference between one element and another? It's not how many neutrons there are, that can vary. It's how many protons there are. Okay, so it's the protons that make up the mass. If you know how many individual protons there are, you can figure out what the mass is going to be for a particular amount of stuff. That's it. That's what mass is. Okay, nothing magical. Now, this is the important bit. Gravity needs the mass in order to present itself as a force. It needs the mass. It needs to be able to alter that space-time. It needs, the mass is needed to be able to bend that space-time, to be able to make that well, so that other things can fall into it. The mass is important. That's why F equals mg. This is not going to happen without the mass. So people often say, is gravity a force? That is an interesting question. It's actually just a philosophical question. Because you have to decide that space-time is only space-time. Because as soon as it has anything in it, a force is created. Okay? Because you can't have the force without the mass. So mass and gravity are intrinsically connected. Gravity cannot express itself without mass. This is evident in Newton's model, it's evident in Einstein's model, and it ties those two models together absolutely. Einstein did not kill Newton's model. It complements it. Okay? All right, good. So let's carry on with this. Two objects have 200 kilograms and 500 kilograms, and their centers are separated by a distance of 25 meters. So here we go. That center to that center is 25 meters. Okay? Now don't forget, when we talk about a satellite range, we're talking about this distance to this distance. So you have to not forget that you have to take into account that the Earth is 12 has a radius that you've got to take into account. Okay, so the Earth has a radius. In this case, in this particular problem, you don't have to worry about the radius because they have given you the distance between the two centers. Now, I want you to think about this. If we have a satellite up there orbiting the Earth, and the satellite is about the size of a car. It's about the size of a small car, all right? The satellite's the size of a small car, maybe weighs 2 or 3 tons, 2,000 or 3,000 kilograms. And the Earth weighs 10 to the 24 kilograms. Do you think it matters about the mass of the satellite? There's such a huge difference between them. The satellite, it wouldn't matter. Does it matter about the size of the satellite when we're talking about gravitational, universal gravity? No, because the size of the satellite is so small compared to the Earth. It doesn't make a difference. All right, so we just say the distance to the satellite. That is good enough. We're not actually concerned about where is the center of the satellite. Okay, that kind of precision is handy when we're talking about when we're looking at the distance from the range, but we don't need to worry about where exactly is the center of mass of a satellite. We do for all sorts of other reasons, but certainly not that. Okay, I'll get into that later. All right, so let's have a look at this. What else do you need? What do you need now to answer this question? You've got M1, you've got M2. Let's write it down again. Fg equals G, M1, M2 over R squared. All right, so you've got all the information that you need because you've got this. G equals 6.67 by 10 to the minus 11. Okay, so off you go. And your answer will obviously be in newtons. Okay, now I want you to think about this formula. And one of the things that I want you to do, not just to answer this question, look at this formula and come back to me with the units for newtons. So in other words, we talk about newtons, we reduce newtons, we reduce that force down to newtons. However, I want you to tell me what newtons are in terms of other things, in terms of kilograms, in terms of meters, in terms of distance, yeah, in terms of kilograms, or in terms of speed. So come up with with what you think newtons will be in this case. Okay, all right, so is everybody clear? No problems? All right, go ahead. All right.